In games with complete information, you remember that we defined the game with the set of players, the strategies for the players, and the utility functions for the players. Now we need to enrich the setting with uncertainty about the types of the players. So this is done in the following. We define a game in a normal form with incomplete information as a longer now tuple where we have the set of players as before, and then we have some source of uncertainty that we call nature, and omega would be the set of possible states of the nature. We don't specify what is that. For instance, nature can be different card hands, and all possible hands would be the possible states of the nature. Nature can be anything, right? So this is the set of possible states of nature. So that's a random variable, and that random variable somehow is translated into the types of our agents. Now, for each agent, we specify a few things. We specify his set of actions, AI. We also specify the type of player I, TI. And this is actually given as a function of the state of the nature. So let tau I function that translates the states of the nature into the type of the agent. Sorry, this is not type, this is set of possible types. So given some state, here, this function is typed agent I. Now given the type of the agent, we define the set of all possible pairs, CI, of the action and the type that an agent may have. Okay, so what are the possible combinations of a type and his action? So it can be the case that AI gives us this superset of all possible actions, and then given what type an agent gets, some of those actions may be available or not available for the given type. Okay, so that's why this is just a subset of all possible pairs. So this is available actions for a player to the entire. Now, given the actions, we have to specify the utility function of an agent, and that also will be a function of the state of the nature and the action played by the player. So this is payoff function of player I. And the last thing that we need to tell is what our agent believes about the distribution of the states of the nature. Right? So there is a probability function, Vi, which is a probability distribution over and that's for every agent I. Now, how does the utility of an agent actually defined given the state of the nature and the set of actions? Say the utility of an agent is then the function of what the state of the nature and what is played by all the players. In fact, what will be my type, the types of all the others, and what we all play. Say if we have all possible combinations of actions and the state of the nature omega, where for all I the pair of action played and their actual type, which is a function of the state of the nature, right? So this will be the type of the player. This is an action that he plays. This action must be feasible, so this must belong to Ci. So for all those combinations, let's call this set L, Ui actually translate such a state into real number, such a profile. All other combinations of the state of the nature and actions will be feasible, so for that we do not specify utility for the player. Now, what is a strategy for a player? A strategy for the player is, given my type, what should I play? So type is something that I get a signal from the nature about, and then given that, I have to decide what to play. So the strategy is actually a function from the set of types to the set of actions. And that should satisfy, of course, that the strategy of the player and his type, that this pair is legal. And that the utility from a combination of strategies will be given as what? Now every agent estimates the probability of each state of the nature given his probability function. Say the utility will be given as an expectation under this distribution, right? So we look at all possible states of the nature given our beliefs about those states, and then we compute the utility given this function. So that's the utility from these given states, and strategy of the first agent given his type, which is given by the function of the state of the nature. And same way for all of the agents. So it's a bit heavy notation, but I think the intuition is pretty clear, right? So once again, we have random variable. That's something that gives externally types for the agents, and then for which we have some distribution, and then we calculate our utility as expectations given that distribution of the space. Now, the notion of equilibrium is pretty much the same, so we just modify the game. So we have a game G hat with the set of agents n as before, and the set of actions defined as the strategy sets in the game with complete information, and the utilities given by this utility function. Now we compute a Nash equilibrium, like normal Nash equilibrium in this game. This will be a Bayesian equilibrium in the original game. The name Bayesian comes from the fact that each agent actually estimates its utilities given the conditional probability on what are the types of the other agents given what is my type. So that's a bias probability, and hence the name. And in auctions, this is one of the standard solution concepts, because it's very often the case that we do not know what are the types of our opponents, but we do have some estimation, some distribution on those terms. Any questions here? All right. So and for a bit of time, for all this, we leave the non-cooperative game world and talk about cooperation. I don't want to repeat the basic definitions. I would assume that you all remember that a cooperative game is given by a set of agents and a characteristic function that to each coalition, to each subset of players, assigns a number, which is the value of that coalition. Right? And we do not specify in a given cooperative game actions of the players, right? So we assume that somehow they know what to do, and by doing that, they receive the value. And the solution of a cooperative game is given by the pair of a coalition structure, how they divide themselves into coalitions, and also the pair of the vector, how they divide the gains that they achieve by cooperation. And then we spoke about the central solution concept in cooperative games, which is the core. And you remember that the core is such a distribution of the pairs where no subset of agents get more than the value of the coalition of the same players if they want to work together. And that's why that means that no subset of players will deviate from that solution and form the coalition pair. So that concept in the form. I will also talked about another solution concept, which is Shapley value. And Shapley value is the way to divide the payoffs, maybe not in a stable way, but in a fair way. Right? And that would satisfy 4 axioms of fairness. today I want to speak about one of the ways that in fact connects the cooperative and non-cooperative games in a way that if we have an underlying non-cooperative game, how can we, if we assume that the agents actually may transfer utilities, say may make side payments to each other, how we can define the corresponding cooperative game given that setting. And one standard way to do that is to look at the coalition of players as, say, a single player playing against the opposite opponent, who will be just the complement coalition, and look at the value of the corresponding zero-sum game. What does that mean? So, once again, we remember that in zero-sum games, the maximin and the minimax strategies and the measure strategies are the same. In particular, that would define the maximin strategy of the agent. So we take a coalition of players, we look at the sum of their utilities in the given game, right? And then we define the utility of the complement coalition as an opposite of that, the negative of that. So that defines us a zero-sum game. We compute the value, we compute the maximum utility of our coalition. So, and that would be the value of that coalition. So once again, the value of the coalition would be how much they can guarantee given to themselves as a coalition, given that non-members of the coalition are against them, right? Want to minimize their utility. So that would give us what is called safety level cooperative games. And in these games, the value of the coalition C is given by its maximum. So we look at to maximize our utility as a coalition. So we look at all possible strategies for the coalition, and our opponents want to minimize our utility, and this is how much we get from playing C against C, where this utility is just given by the sum of individual utilities of all the agents in the coalition. Questions? And then the strategy that we choose to play is the one that maximizes our utility. There are some interesting observations that we can find about these games when they're defined on known families of non-cooperative games. One of them that you know very well now are congestion games. And their subfamily of resource selection games. Now, congestion games are what is called anonymous in the non-cooperative sense of the word, meaning that the utilities of the players are actually given by the partition of those players optimum the resources in the context of projection games. It does not depend on the identities of the players. It only depends on the numbers of players playing this or that strategy. So, non-cooperative games are anonymous if the players' utilities do not depend on the identities of their opponents, but on the partition of the players among different strategies. In the cooperative setting, we would call a game anonymous also if identities do not matter. But what does that mean in the cooperative setting? That means that the value of a coalition only depends on its size, but not on the names of the players. Cooperative game is anonymous if for every two agents I and J, the value of coalition, and for any coalition C, the value of C, if we add I to it, is the same as the value of C if we add J to it. Right, so effectively the value of each coalition only depends on its size. Now, what happens if we take a game that was a non-cooperative game, that was anonymous in the non-cooperative meaning of the word, and define a cooperative game with safety utility values, then the result may not necessarily be anonymous in the cooperative game. For the cooperative game to be anonymous, we need another additional assumption. We also need the underlying non-cooperative game to be symmetric. And symmetric means that the utility functions are actually immune to permutations of the agents. So that the utility of agent I from playing strategy C1, C10 would be as the utility of some permutation where the strategies are permuted. So that's symmetric. Now we can show some facts about such games. First of all, monotone. Monotonicity means that the value of a subset of a coalition is no greater than the value of the supercell, right? Why is that true? Any intuition? So what's the value of the coalition? The value of the coalition is the maximum that members of the coalition may guarantee, can guarantee to themselves if the others are trying to play against them. So if I look at coalition C prime, then the opponents and in fact the enemies of that coalition is the rest of the players and minus C prime. Now C is the bigger coalition. Now part of the agents of that coalition decided to cooperate with the members of C prime. As a result, the value of the coalition can only grow. So we can write C as C prime and D, right? If when we calculate the value of C prime, D play against C prime. When we calculate the value of C, D play for C and C prime in particular. So the value of the coalition. Have a cooperative game which is canonical, and the core of that game also is non-empty. So if for anonymous cooperative game with a non-empty core, we can easily find at least one member of the core, and you can actually make a guess at it. Value of the ground coalition and just evenly divide it among all the players, this will define the core payoff. But that given that the core is not empty, because it can be empty, and then this payoff will not be element. More than that, the payment, the symmetric payment is also the Shapley value in such games. Now, that's given that the game is anonymous, and indeed, when we look at congestion games, symmetric congestion games, they define anonymous cooperative games with safety level values. And some of these facts will hold for those games. But they are, once again, conditional on the core being non-empty.